Hi, this is a basic tutorial for the Hydrodynamics module in Shape version 5, where we're going to show the basic and simple features of this module using a supernova explosion. And here we have shape in the Hydrodynamics module, which we open by clicking on the liquid splash icon. And we have the most prominent feature of the module is the viewport, where the preview of the simulation will be shown. At the top we have several icons. The calculate icon is the one that we click when we are going to run the simulation. There's an add button where we can add several more viewports, which will display different variables and aspects of the simulation in real time as it progresses. A refresh button, which is needed when we want to refresh this display when the simulation is actually paused or stopped. We have two options for how the windows are going to be configured if there's more than one, and each window, each viewport will have its own icon at the right. Now we are going to start with only one of these windows. On the right we have several tabs that have parameters for the simulations and the visualization. First, the general tab, which has the basic grid size of the simulations. We're using a square grid with uniform spacing. In this case, to speed it up on this computer, we are going to use only 80 cells per side in the grid. So the grid size will be 80 cube. Currently, the only solver that can be used is a fun layer solver, with fun layer splitting. There are two options for resuming simulations when it has been stopped or has been loaded from the previous state from disk, and an animate option, which we will get to in a later tutorial. At the bottom we have status area, where the current physical time of the simulation is shown, which step number we are at, and the current time step size of the time step. In the second tab, the flow tab, we have basic flow parameters like the Coulomb number, the gamma value for the simulation, a artificial diffusion parameter, the minimum temperature, and when the simulation should stop in terms of the physical time or the number of time steps. It will stop when either one of these is reached first. And then there is a cooling error and two parameters for the cooling, one enabling the cooling and a coefficient that controls how much of the hardwired cooling curve is going to be used in the simulation. One means, of course, the full cooling will be used. And the next set of parameters is concerned with the boundaries at the edges, where we can select each side changing from outflow or reflection condition. The camera tab controls the visualization in here, where most important is the image size, and there are parameters for the variable that is going to be displayed. In this case, first we have a look at the pressure or the density, speed or temperature. These are the options in here. And by clicking on the viewport, I will select the one for which these parameters are working. Then there's a tab where we can select various filters, add new filters that have been set up earlier in the filter module separately. These filters are enabled or disabled in the filter module. We can add new ones that have already been set up, or we can eliminate any filter from this list. And the output tab, in the output tab we can load grids that have been saved, or save the current hydrodynamics grid for later use and reloading for continuing the simulation or for visualization of a certain state. So that is the basic setup of the Hydro module. To start a simulation, it has to be set up first in the 3D module, where we basically set up the structure of the initial conditions and internal boundary conditions. In this case, we have three different objects: one for the ambient medium, one for the actual explosion, the initial condition of the supernova, and a render object that is only used for rendering in the render module. So the ambient medium can be set up as any of these initial structures that we can, primitive structures that we can have. And its size and location doesn't matter, because it will always be filling the whole domain of the computation. And selecting ambient medium, or generating this object first and then giving a suitable name like ambient, we add the basic hydrodynamic modifiers that we need. And the most important, in a way, is the hydro modifier, which has only a drop-down list, which is given by a background, has an initialize and a boundary value. Selecting the background, this means that this object will have the parameters for the whole initial domain of the computation. We give it a density, which is set up in the usual way, using magnitude, texture if we want. In this case, we use a magnitude that is determined by parameters given in the math module. We can see that in the function, where we use analytic, and we use a single density for the environment. It is a constant density in this environment, and this variable is given a value in the variables tab. And since we have applied the use global variables button, this value is actually taken from the math module. We will have a look at that in a second. The velocity in this case is set to 0, which is seen here because of the f0 value in the general area of the velocity modifier. The linear increase here is not applied, since we multiply it by a 0 value. We could have just as well set all the values into 0 here. Okay, similarly we need a pressure. The pressure value, the pressure modifier, is also taken from a global variable, which has been set up in the math module. Single value. Okay, this is all for the parameters that we need for the environmental setup. The explosion is very similar. In this case, however, the hydro modifier is set to initialize. This region does also have a certain size, which in this case is set to 3 parsecs, which is a small fraction of the whole domain, which is actually 50 parsecs wide. And okay, density similar to the ambient medium. We take a value from the math module, the global variable, and so forth. For velocity, velocity is also set to 0, and pressure again takes a global variable. Okay, now let's go to the math module. Here in the math module we have set up the basic astrophysical and atomic constants that we are going to use, and then a set of variables that are specific to the supernova explosion, like the gamma value for the hydrodynamics. This is the initial radius of the supernova explosion, set to 3 parsec. The number density in terms of numbers per atoms per cubic meter. Remember that we're using international SI units. The environment temperature is set to 10,000 degrees. The density in the environment is set to the number density times the mass of the proton times 0.6, meaning that we take into account that the medium is fully ionized and there's a little bit of helium in there. And the density of the supernova is then set to the environment density plus 1 solar mass within the volume of the initial radius of the supernova, which then computes the final density that is taken as the density of the initial supernova in the 3D module. Then we have a total energy of 10 to the 51 ergs. We're using the variable erg, which we have defined at the top, which converts our ergs into joules, which is our energy unit in shape. And then we compute the thermal energy that is then used for computing the pressure in the supernova. And then the pressure in the environment is computed from the environment temperature and the Boltzmann constant and the number density. These variables are then used as global variables in the modifiers as we have seen. Now there's one more number that we need in the render module. Go to the render module and open the image tab, and the only thing we have to do in the render module is set up the size of the ambient medium, the computational domain, which in this case is 1.5 times 10 to the 18 meters. Alright, and then we can go back to the Hydro module and click on Calculate, and hopefully the simulation starts without major hiccups. It initializes the background, then the hydrodynamics, and then starts to show values for time and step and how much one time step is, and the calculation starts and shows the visualization. And since we have a reasonably small simulation in here, 80 grid size of 80, this goes rather fast. And we can change, for example, from pressure visualization to density visualization. Now we have a projection of the full grid. If we use our mouse and left click and drag the mouse, we can see that this is actually just a plane as it rotates around in real time. And here are the rotation. In the camera display, we have the rotation values in degrees. We can reset these to 0. Now we have a plane because there is a filter, 2 filters in here, which select this plane. Actually, one of these filters is disabled. You can see this in the filter group. Here the Y filter is disabled, and only the positional Z filter is disabled. It limits the visualization to a small area in the middle of the, or a plane in the middle of the domain. And we can see how it expands. This low resolution computation makes the expansion of this presumably spherical simulation rather square. But otherwise, it looks good and expands as expected. We can add another visualization here and set the camera value, the image size value to 80, so it is actually what we have in the grid. And set the visualization to temperature, for example. This is now what the temperature is throughout the cut. And we can look at the image simultaneously by clicking on the tile distribution and wait for the computation to continue until we're finished. Thank you. That will be it for this initial introduction to the Hydro module. We're going to do more tutorials to look at more detailed visualizations and how to render and display these in the graph modules and the render module. Thank you.